Hi, I'm Christa van IJzendoorn. I'm a PhD candidate at Delft University of Technology, and I'm super interested in aeolian sediment transport. And that's because I want to predict how coastal dunes will develop in the future. And for that, you need to know how much sand will end up in the dunes. Well, today I'll be talking about the effect of marine and aeolian processes on vertical grain size variability in the intertidal area. The intertidal zone is located in the area between the high water line and the low water line. And we know that in this zone marine processes can act, and during low water, when there's enough wind, aeolian processes can act. Well, together these processes interact and cause a lot of variation in the intertidal zone. And we know that the intertidal zone is very important for aeolian sediment transport because of these variations. For instance, moisture content varies a lot, but also grain size. And that's what we're gonna focus on today. When aeolian transport occurs, fine sediment is most easily moved by the wind. So when the fine particles are removed by the wind, coarse particles can stay behind, which can coarsen the bed surface. Marine processes can cause mixing due to the energy of waves and the energy of swash moving the sediment around. And this can cause the grains at the bed to be mixed and become more uniform. Well, in this study, we want to test whether these assumptions are correct, whether marine processes really cause mixing and aeolian processes really cause coarsening. However, for this, we really need a new method to measure vertical variation in grain size, because currently we use grab sampling, and those samples usually consist of the upper 5 to 10 centimeters of the bed. And then we assume actually that there's no variation in those 5 to 10 centimeters because, for instance, we only determine one D50 value. So what we did is make a completely new device. It's custom made, it's super cool if you ask me, and with this we can measure that vertical grain size variability. In the lower right you can see the bottom plate that's put onto the surface, and then we insert this device into that bottom plate. And what you can see is in this movie is that we're scraping off really the upper layer of the sediment surface. I move the scraper around, and we're scraping off the sediment that gets collected in a sampling bag so we can take it to the lab and analyze the grain size. Well, the sand scraper has a dialing mechanism that's of which the depth scale you can see in the upper right image. And we can scrape off layers with a resolution of 2 millimeters vertically. And we can scrape up to 50 millimeters, so 5 centimeters. In the lower right you can see that when we're done, we leave a bit of a hole behind because we're really removing the sediment. We applied this new method at 3 different field sites. One in Walport, Oregon on the west coast of the US, then 2 on the east coast of the US in Duck, North Carolina, and 3 in Noordwijk, the Netherlands. I want to show you an example from Noordwijk to make sure that you understand how much data goes into this, and how we can visualize what we're collecting with the sand scraper. First of all, the upper 2 millimeters. You can see the D50, that's a vertical gray bar, but also the color of the box plot is the D50, which is here around 280 micrometers. Then the box plot borders are the D25 and the D75. The D16 and the D84 are indicating the whiskers. All the details of this are not super important for now. I just want you to remember that when that box plot is wider, the distribution of the grain size is wider. So there's a larger contribution of finer grains and coarser grains. And depending on the width on either the right side or the left side of the D50, if it's on the left side there's a lot of fine grains, and if it's on the right side and it's wider, it's a lot of coarse grains. Here we see the next layer of this cross section. It's a little bit finer, lighter color, and then up to 8 millimeters it's a little bit coarser again. Oh, but here it really changes. This is the layer from 8 to 14 millimeters depth, and it's quite a lot coarser actually. We see the same for the layers after that, up to 32 millimeters. So this shows us that we can see the vertical variation in the grain size. What we actually did at this location is repetition sampling. We took this one sample, but we also took a sample very close by, 1 to 2 meters from this sample, and we did the same, just the same again. And we did that to make sure that this method is repeatable and that we trust it. And what we got from that repetition sampling was the following. So we see here again the cross section of the sample, and if we compare them, we have similar gradients. So at the top we have finer sediment, and underneath that some coarser sediment, which is promising because this shows that the same method in nearly the same location shows similar gradients. Well, we actually also did this in duck, and here we see that their grain sizes are much coarser than in Noordwijk, and they're pretty similar throughout the cross section. And I want to point out that we have two gradients here, with somewhat finer sediment on top, then some fining, and then some coarsening again. Well, overall, these variations of the grain size are in the order of 5 to 15 micrometers. And vertically, we see changes over up to 6 millimeters. So those are pretty limited, and we are expecting that the temporal variations due to the marine and the aeolian processes will dominate over this. But how are we actually going to measure the influence of the marine and the aeolian processes? For that, we're really going to need a sampling strategy, and I'm going to walk you through that. Temporally, you can see in the upper image a tidal cycle with high and low waters. And then in the lower plot, you see it spatially. So if we would be in the field, this would be the intertidal zone. We know that during high water, the marine processes are acting on the intertidal zone, and during low water, the aeolian processes can act if there's enough wind. Well, to measure that, we can actually measure before and after the aeolian processes acted on the intertidal zone, so before and after high water. And then we can do the same for the aeolian processes by sampling before and after the transport, so before and after the low water. Well, you can do that for one location, but we actually did it for 3. And that looks like this. Because of the increase in water level and decrease in water level, the timing of those 3 locations are a little bit different than when we're just looking at one location. Next to the sampling of the vertical grain size, we also looked at elevation change. We have GPS measurements, we used a LiDAR in duck, and in Waldport we actually used erosion pins that showed much more detailed, in the order of millimeters to 1 to 2 centimeters, what kind of variation in elevation occurs near the bed. this results in a lot of experiments and a lot of data. We had 3 field sites with, for each of them, multiple locations with 3 locations and then 10 samples up to 5 centimeters depth. So a lot of grain size analysis, a lot of sieving in the lab, and a lot of data analysis. I want to save all the data for my paper, but for now I want to go through some of the results we got from Waldport, where we show marine and aeolian influence and actually some bed forms occurred. First of all, we measured the elevation before and after high water. Gray is after high water. And we see the high water line. This is where the max swash excursion was measured. And we see that location 3 just got hit by the swash. And at location 2, most of the morphological change took place. And I want to walk you through all these locations and the measurement times we had for them. Location 1, we see quite some variation in the vertical, with some wide grain size distributions. Then after high water, those wider grain size distributions reduce, and we actually see that the grain sizes are a bit more uniform, which could be possible due to the marine mixing. For location 2, we saw a very nice gradient, so coarse material at the top and then fining downwards with some coarsal material below 38 millimeters. After high water, however, we see a bunch of change. We see wider grain size distributions and a clear gradient is gone. And that could well be related to morphological change, because there's a lot of sediment movement when that happens, and that could result in these big changes in grain size. Then for the third location, we had some nice, fine, uniform grain sizes before high water, and during high water there were only a couple of swash excursions that reached this location. And we see that that only changed the upper layer, and that got much coarser. Well, after aeolian transport, because this was actually the only location where really aeolian transport took place during low tide, we see that that coarse material is still present, but there's a fine layer of sediment on top. And if we zoom in, this measurement was actually taken on the crest of one of these aeolian deposits or aeolian bed forms that you see in the right figure. If we schematize that, we can see that this measurement was taken under the crest of that bed form, and it was a meter scale bed form. And the elevation was in the order of millimeters, because we actually measured some deposition with the erosion pins, up to a centimeter. And we collected the vertical grain size in the trough as well, just to see what the difference would be. And we see that the coarse grains are present in the trough, but there is no fine sediment on top. So where we expected coarsening due to aeolian processes, there's actually also fining happening due to aeolian deposits in the intertidal area. Well, we had these assumptions that marine processes cause mixing and aeolian processes cause coarsening. I want to leave the full discussion of this to my paper, because there's also the data from Duck and Noordwijk. But for now I want to conclude that we can indeed show that the marine and aeolian processes have significant impact on the vertical grain size distribution. I also want to conclude that we actually successfully applied the sand scraper. This was a completely new method, and we've been able to show that there's vertical variability in the grain size. And then as a takeaway message, the measurements with the sand scrapers are a big improvement compared to grab sampling. We see the vertical variability, and we no longer have to assume uniform grain size in those upper 5 centimeters. Because that uniform grain size is really a simplification of reality. If we would visualize it, we would have a big orange blob, and now we've shown that there's actually a bunch of fine and coarse sediment present in there. So next time when you're on the beach, remember that it's not just one uniform grain size that you're walking on, but the tapestry of layers of finer and coarser sediment. Thank you very much, and please, if you have questions, you can find me in the session that I listed here, or please send me an email. I'm very interested to talk about this. Thanks!